Hi there, in this video we're going to explore the derivative of some trigonometric functions, starting off with sine. Now in other videos they take an algebraic approach to explore it thoroughly. We're going to look at it a little bit more briefly, I suppose, by using a graphical approach. So that means we're going to look at a picture of the graph and see whether we can make some conclusions. Very, very quick reminder about what derivatives are. We have a function, and the derivative of the function describes the gradient at a particular point on that function. So if we remember that a function is simply a rule which describes how an input, the x, maps to an output, the y value, and then if we draw it as a picture, then this line represents all the x, y points that make up that function. The derivative gives you the gradient at that point. And that means that if we pick a particular point and draw a line which a straight line which touches the graph at that point and only at that point and keeps going, then that is just defined as the gradient at that point. And remember that gradient is simply rise over run. So the gradient function is the derivative, and the derivative is the gradient function. And the gradient function is simply the rule which describes for a particular function that when I input x, the output is the gradient. Okay, so that's like a few lessons worth in about 30 seconds. So if you don't remember, look up about gradients, gradient functions, and derivatives. In this screen here, you can see this red line represents the trig function sine, that beautiful sine wave that's going up and down. I've got it between -2 pi and 2 pi. And what I have over here on the left here is I have d of x, not defined yet, but that's going to be the actual derivative, what happens when I f dash of x effectively. And g of x here is the gradient function. Remember, the gradient function and the derivative is the same thing, but here I've defined the gradient function using the fundamental first principle of f of x plus h minus f of x. So that's rise, because f represents the y values, over h, which is the run. Remember, it's x plus h minus h, which is equal to, x plus h minus x, which is equal to h. So it's rise over run. Don't forget that. It's a function because rather than looking at a specific point like the point 0 or the point 1 or the point 2, it uses x instead. Now, f has been defined up here as sine of x. So effectively, I could replace the f with sine, and it would have sine of x plus h minus the sine of x over h. So this defines the gradient at any given input here. So whether x equals 0, x equals 1, x equals 2, etc., this would give me the gradient at those points. I've got a slider here because we know the way limits work is that we define the gradient as this function here as h approaches 0. Okay, so what I'll be able to do is I'll be able to slide this down to 0 so we can get a sense of it in a moment. Before I do that though, I've also got a table of points I haven't filled in yet, and we're going to do that as our first port of call. So it's just, you can see it's g of x here is the gradient function. I've chosen a series of x coordinates here from 0 to 2 pi, okay, just in pi and 4 increments, and then I'm going to work out what the corresponding gradient coordinate would be. So I'm just going to be putting in 0, g of 0 here, for example, and we can see that there's a point there. So what does that mean? It means that if I look at the gradient function, I've now substituted 0 for x, so I've got sine of 0 plus h. So that's the sine of h minus the sine of 0 all over h. And that gives you the point here. And as I slide this down, we can see that point is approaching 1, like so. Okay, so that's that. I'll keep on doing the same for each of the points, and let's see if we can't work out what these are plotting out. So I'll just quickly do that by copying and pasting. The input is pi on 4, so g of pi on 4 would be the output. And there's a second point there. Pi on 2, g of pi on 2, 3 pi on 4, g of 3 pi on 4. And we're finally up to pi, which is what, 180, isn't it? So there we go. We've got this sort of funny old thing happening. We'll keep going. These are just in 45-degree increments between 0 and 2 pi. And I'll just finish up nice and quickly. And there we go. So we've got it going sort of higgledy-piggledy down and higgledy-piggledy up a little bit here. And that's only because we've used a really rough value of h equals 1 here. So that's not particular. We know that the gradient is not defined for h equals 1. It's defined as the limit as h approaches 0. So in order to get a closer idea about what shape this is creating with these simple points here is to drag h down to 0. So if I make h equal to 0, it won't quite work. But you can see what's happening with these points as I shift down. So they're kind of almost lining up, aren't they, symmetrically for a bit. Away we go. We're still going down. And I'll take it as far as 0.01 to see if you've got a sense of what these points look like. So we're here, and then we're going down to here. Then we're going down to here, nearly pi on 2 there. It's nearly an x-intercept. Down to here, then up to here, then up to here. I'm going to ask you to pause the video and have a little think about what these points look like to you. Do they look like anything you've seen before? If you did a dot to dot on them, join those dots up, would you get something which looks vaguely familiar to you? So pause the video and have a think. Okay, did you pause the video? I'll give you another wait. All right, okay. So there's a point there as well, which you can't quite see. Maybe if I do that. No, it doesn't make it any easier. Okay, so you've got these points here, like so. I wonder if you had a sense of what this graph would be. If we now select the, if I now turn on the gradient graph, I'll shove it back to 1 just so that we can sort of see. The gradient graph will join those dots for you, but because it's a continuous function here, it's also made every single dot in between. And yep, might be a surprise or may not be if you figured it out from just the dots alone. It's made a nice sine curve here, a sinusoidal curve, I should say, here as well, like so. But it's clearly not sine. And if I move h down, can you see what's happening with those points? Can you see what's happening with the line? It's going closer and closer and closer to what function, I wonder? I'll go as far as 0.01. So if I zoom this in, this would not be the same as what g of x is, but it's getting really close. But look at this, we've got this lovely cup shape from 0 to 2 pi, and reverse, we've got this lovely cup shape, or wine glass shape maybe, from 0 to negative 2 pi backwards. So what does that remind you of? I hope it does remind you of cosine of x. And now that I've filled it in, you can see it basically overlays that graph, of the gradient graph. So what does that mean? That means that as h approaches 0, sine of x plus h minus sine of x over h approaches cos of x. So the derivative of f of x is equal to the sine of x, is equal to the cos of x. I'll say that again. The derivative of sine of x is equal to cos of x. If I add in a new graph here and I just say f dash of x, I think I can do that. Change the color. I'll make it little dots and purple. Make it green. You can see that f dash of x is the same as the cosine of x. It's the same line. Okay, so graphically, I hope that sort of gives you a sense of why f of x is equal to the cosine of x. Alrighty, so that's the cosine of x, sine of x, and the derivative is cosine of x. Let's do something similar with the cosine of x. So you can see here that I've got g of x as the gradient function of cos of x plus h minus cos of x. It's the purple line. So the red line again, this time the red line represents the cosine of x. So we've got the cup shape or the wine glass shape, like so, or the tulip shape maybe might be a nicer way of putting it, like so. And if I look at the gradient graph, there it is there, just another sinusoidal line, but where's it going? So let me drag this down to as close to zero as I can. You can see that it's certainly racing down, racing to a familiar shape, but not quite. I mean, we've got a rise up here, we've got a rise up here. It's hitting zero. So if you think about it, how about I just pause the video? I'll turn this off for a second. This is cosine of x. So you're just looking at the gradient function, i.e. the derivative of cosine of x. Maybe give you a moment to see if you can figure out exactly what you're looking at there. Okay, so hopefully you paused it and now you've returned. Did you get something or not? Pretty well much. When I look at the axes here, I can see that this is going to be hitting zero. So if it was a cosine graph, I would be expecting it to be either hitting 1 or -1, or depending on how it's been, unless or it could be translated, but more or less that's kind of what I'm looking for. But this is hitting zero, which gives rise to the thought that it might be a sine graph. But a sine graph, very quickly, looks like this. So it goes up and then down and then up again. But this one's going down, then up and then down again. So it's doing exactly the opposite of what we would expect, right? So what does it mean when something is reflected about the x-axis? We can see that this purple bit here is just a mirror of this bit here, and this purple bit here is just a mirror of this bit here. So it's being reflected about the x-axis. And what does that mean? It means that the function must be negative. So all the y values then get reversed in value. So where y was positive, y is now negative. Where y was negative and negative makes a plus, it's now positive. So it's reflected about the x-axis. So we have y equals sine of x, negative sine of x, and then it's perfectly on top like so. So what we have here is that the gradient function is sine, but reflected. There we go. So there's the original function. D of x is the derivative function, which is the same as f dash of x, like so. And I'll make that dotted so that we can see it. We can see that the derivative is this dotted line. D of x equals negative sine of x. It follows those dots. That's because negative sine of x is the derivative of f of x. So there you have it. We have two functions. We have the derivative of sine of x equals cos of x, and we have the derivative of cos of x equals negative sine of x. There's one trig function left, and that is tan. So here's tan of x. I haven't filled in the derivative yet, but we can have a look at what it looks like from the first principles approach, tan of x plus h minus tan of x over h. So if I tick that, there it is there. And if I move it down towards zero, that'll do. we can see that it's got this loopy thing happening here, like so. If I just zoom out a bit, it'll look even more crazy. So I've got this loopy thing happening here. Can you work out what function that might be? No, of course you can't. I couldn't either. So I'm going to give it to you straight up. The derivative function, in other words, the gradient function of tan of x is 1 over cos squared of x. So you can see if I turn it off, there's the derivative function, there's the gradient function. They are the same function. So 1 over cos squared of x. Now, although the algebraic working out of sine and cosine is actually quite tricky to look at, the working out the derivative of tan isn't as tricky. So what I'm going to do after this video is create a second video where we'll have a little look at how we might work out algebraically where this 1 over cos squared x comes from. But that'll do for today's video.